Now, let's understand some practical cases that can occur. Okay. So, as we saw that the orbits can be elliptical and they can be oriented differently these orbits can be oriented differently with respect to the observer. What do we mean by different orientation? You see, this is an elliptical orbit of a two-star system. This ellipse and this ellipse and this ellipse and this ellipse, they are practically all the same. You have the same set of stars, you have the same set of orbital parameters. But here, this is your observation, this is a line of observation, okay? Here, this is the line of observation. You can say, this is the line of observation, here, this is the line of observation, okay? So, depending on which orientation you're talking about of the ellipse, okay, which is the focal point that you are oriented towards, that determines the visible parameters that you measure. So, look at it here. Here, what happens when this object is at 1? Okay, this is my object, and this is the position 2. Okay, here this is my position 1, this is my position 2. Okay, so this corresponds to the first eclipse, this corresponds to the second eclipse, right? Here, this corresponds to the first eclipse, this corresponds to the second eclipse. Okay, similarly here, this is my first eclipse, this is my second eclipse. Okay, and here this is my first eclipse, this is my second eclipse. Okay, now in this particular situation, this situation and this situation, what do you see? That the difference between the two eclipses is equal to p by 2, where p is the total time period, total periodicity. Okay, both here as well as here, when the orientation angle is 90 degrees or 270 degrees. Okay, but here what happens? The difference of the two eclipses is less than p by 2. Why? Because this time taken is shorter than this time taken. Whereas here this time and this time are equal, here also this time and this time are equal, right? So, in this orientation, if you are looking at it, and if you measure that T2 minus T1, that the time gap between these 2 points is less than the total periodicity, then you know this is the orientation of the eclipse. And when it is like this is my 1 and this is my 2. So, here there is a typo out here. Okay, it should not be T2 minus T2. Okay. So, when this T2 minus T1 is greater than P by 2, then this corresponds to this particular orientation of the ellipse. So, now looking at the light curve of these eclipsing binaries, looking at the points of minima, you can actually measure the orientation of the ellipse. And what we actually mean by orientation of the ellipse is that how is my foci of the ellipse oriented towards the line of sight, and what is the relative position, with which we are measuring these binary parameters. So, these are different examples of your eclipsing binary light curves. Here you can see that the two stars are nearly of the same size, right? So, when the two stars are nearly of the same size, but the spectral type is not exactly the same. When that happens, how do you measure that the two stars are nearly of the same size? It is because the point of second contact and the point of third contact, they are nearly the same. And hence, the duration for which you see the minima is nearly equal to 0. The light curve is nearly a triangular light curve, right? But we can measure from here that the spectral parameters will not be the same because the luminosities of the two stars are not exactly the same. And from HR diagram, we know what is the relationship between the luminosity and the spectral type. So, because the amount of light that is getting eclipsed is different out here, we immediately know that the luminosities of the two stars are not the same. Here, the more luminous star is behind. Here, the less luminous star is behind. But because the second and the third contact are very close to each other, it's nearly a triangle, the sizes are nearly the same. In this particular case, what happens? The sizes are different, and hence the point of second contact and the point of third contact, they are not coinciding. At the same time, the luminosities are different simply because the total amount of light blocked in this particular case is different. And from there, we get a measure of the spectral parameters from the HR diagram. So, this gives me a very, very good observation of the binary star systems, which are very different in their physical parameters, which includes the mass and the size, and correspondingly the temperature, the luminosity, and the spectral type. Then there are many other effects also seen in the eclipsing binaries. For example, here you can see the tidal effects causes distortion in the shape of the star. It deviates from being a spherical shape. Okay, and this deviation in the spherical shape you can see in the nature of the blocking of the stars. If there are two spherical shapes crossing each other, then you see kind of very discontinuous eclipse happening out here. When this is becoming more curved in nature, okay, that means that your shape is deviating from the circular shape that you see out here. So, and that happens due to the tidal nature. What is a tidal force? Tidal force is a force acting on a large body where the force on one end and the force on the other end are not the same. And hence, when gravity is acting on the on a same body, but the two surfaces are experiencing different amount of gravity, then the two surfaces will be not changing in the same manner. And hence, the two surfaces will get deformed with respect to each other. So that is what we mean by tidal disruption, and that is what we see out here. Now, we will talk about this particular system later, maybe in some other time, but this is a very, very important star. So I thought I'll just mention this particular star system separately. This is known as the Algol system, okay, and it is one of the earliest eclipsing binaries that was observed. And of course, this is the nature of the light curve that you see from this particular star system. Okay. Similarly, let's look at some other special eclipsing binaries. So one of these is AR Cassiopeia. Okay. In AR Cassiopeia, you see this is the nature of the eclipse that you're looking at. So you should realize that, both the stars are nearly the same because the amount of eclipse that you are getting is the same. At the same time, they are deviating from this, discontinuous shape of the eclipse that you get out here. So there is more tidal effect coming to play out here. In Algol system, you see the shape of one of them is kind of resolved whereas the other star is perhaps deviating from the spherical shape. Okay? And the amount of light that is getting eclipsed is very different. This is very, very interesting. Maybe we'll deal with algol later. Okay? This is mu Hercules. Here again you see there's lot of deviation from the spherical shape of the two stars out here. Okay, so on the left again you have the schematic representation of the two stars that you get out here uh, in these three different systems. Okay, now we will talk about few very, very important effects that you see in an eclipsing binary, which you do not see if you do not see the eclipsing effect. One is the limb darkening effect. You might have come across the term limb darkening in connection with the flux observed from the sun. You see, when you look at the sun, the center point appears much brighter than the surface. And that is because the amount of light that is coming from the center is coming through many layers, whereas the amount of light that is coming from the surface is coming from very few layers of the sun, right? So this effect occurs for the stars also, and hence when you are looking at the edges of the stars when they are getting eclipsed, it is deviating from what you assume from a uniformly illuminated circular shape, because the edges are now dim, and that effect you see when you see at these kind of features near the contact point, the first contact, fourth contact, you see this kind of feature. In the second and the third contact, you see this kind of feature. Okay. Similarly, you see in the second occultation also. Then, very often, more often than not, your inclination of the orbit is not exactly parallel to the line of sight. You are at a certain angle. Again, simply because of the random distribution of the systems in the universe. So, in that case, what happens? You will not see the whole occultation. Only part of the star gets obscured, right? And hence, what you will see is not a full triangle. Of course, these effects are due to your limb darkening effects and all, but then in the end, you don't see a full triangle coming, or you do not see the whole of the one star getting eclipsed, because ultimately from these relative sizes you get to measure what is the luminosity, and from the luminosity you have a measure of what is the size or the parameters of the star, right? So you have an estimate what should be the extent of time between the second and the third contact. But when you see that it is not happening, but you expect that to happen, this can only imply that you are unable to see the complete transit because it is at an inclination. Okay, the other star is blocking the main star only for a certain amount of time, small period of time, simply because of the inclination effect. Okay, so this is a very, very common effect you see in eclipsing binaries. Then very important is the reflection effect, because what happens out here, you see, this total light doesn't remain constant. It is supposed to remain constant, right? So what happens is that one star reflects the light from the other. Okay? So basically what happens in this particular case is that your smaller star, when it is going behind, it is the light that you see is not just the sum of the two circles that is emitted towards you, but at the same time, some light from the bigger star is getting reflected by the smaller star and coming towards you. So this is known as the reflection effect, and hence you see that the total light, which should remain constant, doesn't remain constant, it increases like this before the second star gets obscured. Okay? And of course, the ellipticity effect, which happens due to the tidal effect, the tidal forces. So here the shapes of the stars are getting distorted, and hence this is the nature of the light curve that you see. Okay, because now you are not occulting a circle, you are occulting an ellipse. Okay.